Okay, so this is going to be part 1 of 1.2. This is functions and their properties. And a function is defined to be, we usually call them f of x, but it means for each x, there is one y. We're used to testing functions. You've probably seen these things like x, y, or domain and range, or domain and range. Each one of these goes to 1. Those two both go to 2, which is fine, but each one can only go, I can't have 2 lines out of either of these. You're probably also familiar with the vertical line test. Oh, hey, a vertical line here crosses more than once, not a function. Okay, domain. Domain stands for the values that x can take on. Anything that is legal for x to take on. Because we're dealing with real numbers, we're not going to have complex numbers, so there's a couple of things that you can't do. Kind of 3 in math. One of them is divide by 0. So if a value of x causes division by 0, it's not in the domain. Number 2, we cannot take the square root of the negative number within the real numbers, which is what we're mostly dealing with. So if x would cause a square root of a negative number, that's not in the domain. And my last thing is I can't take the logarithm of 0 or a negative. So if x values within logarithms when we get to it. Those are kind of the 3 things that cause domain errors. So if we look at example 3, we're going to start with finding domain of these functions. F of x here is equal to the square root of x plus 3. So I know what's in my square root cannot be negative. It can, however, be 0. So if x is a positive number, this is positive. If x is 0, it's positive. If x is -1, I've got square root of positive 2. That's fine. If x is -2, square root of 1, that's fine. If x is -3, square root of 0. That is 0. That's okay. However, by -3.1, I've got square root of -0.1. That's not okay. So my domain, I'm going to write this in interval notation, is -3 to infinity. I could also write that as x is greater than or equal to -3. We like to write domains in Precalc in interval notation. It's pretty quick and easy. Here I've got a square root. Well, I know it's got to be 0 or larger. I also have this problem, though, that I can't divide by 0. And if I plug 5 in for x in my denominator, 5 minus 5 is 0. So I have to exclude 5. When I do interval notation, I can do that by doing 0 to 5, not including 5, union 5 to infinity. Okay. And my final one, oops, a of s. A of s equals square root of 3 over 4 s squared. Now the square root doesn't have a variable in it, so I don't really care. I can square anything. There's no restrictions on squaring, so my domain is all real numbers or -infinity to infinity. Range, on the other hand, is y values. And to find range, you pretty much need to graph. I'm just going to show you what this graph looks like. You would probably use a graphing calculator to make it. But I can see here that it looks like as I go out, it's getting pretty darn close to all of these. But it looks like a rational function that's going to have an asymptote at the x-axis. In fact, 2 divided by, as x gets larger, I get closer, like a million. 2 divided by a million isn't 0. 2 divided by negative a million is not 0. My range, my y values can be anything. They're going to go forever up and down here, except 0. So I do negative infinity to 0, but I don't include 0 because it can get infinitely close. Negative 2 a millionth is real close. Negative 2 100 millionths is even closer. And then on this other side, the y value starts just above 0. And yes, it is way out on the right end, but I'm looking at the vertical values here for my range. Ranges we're going to figure out through the process of using the graph and finding out where the y values or the vertical values are and aren't. The next thing we're going to talk about is continuity. That last graph, continuity means can I draw the whole graph without picking up my pencil? This one is no, I kind of jump up here. Okay, that is what we call a discontinuity. There are other types of discontinuities. Sometimes you can just have a hole in your graph. Okay? Sometimes you have jumps. You have a graph that looks like this, where it suddenly just jumps to a higher value. This one, a hole, is known as a removable discontinuity. And that's because we could use a piecewise function and plug in that hole. Continuity. I should try to spell that right. This one here is called a jump discontinuity. And my last one looks something like what I had on the last graph, is called an infinite discontinuity because it goes to infinity on both ends of it. Certain functions are increasing or decreasing, and we can give those in intervals: increasing, decreasing, and constant. We'll be pretty clear on this one. I am increasing, constant, then decreasing. We'll call this point here 4. So I'm increasing over in this part way on the left. I'm going to put a blue mark by it. And that goes from negative infinity, and I always map with my, looks like a funny infinity. I always map with my x coordinates. I don't care what the y coordinate with it stops increasing. I care what the x coordinate is. And I should include 0 for my increasing point. Remember, negative infinity, we never include. I then go constant from 0 to 4. Yes, I'm including 0 in both of these because it doesn't change. It goes all the way to 0. It's increasing all the way to 0. It starts being constant at 0. And then it starts decreasing. Again, I include 4 because it gets smaller from 4 to infinity. I usually abbreviate increasing, decreasing with inc and dec. You are welcome to use those to have to write less. So we can identify discontinuities. A removable discontinuity, let me give an example of that, could look like, we'll do one here. So if I chose to simplify this one, I can factor that numerator into x plus 2, x minus 2, and my x minus 2's can cancel out. Do that a little differently. Leaving me with something that functionally looks like x plus 2. So if I were to graph this, the issue here is that if I were to graph this, I would just have a line. The issue here, though, is that 2, my function doesn't exist. My original does not exist. And so I end up with a hole in my graph. The reason we call this removable is I could create a function g of x that's basically the same function. X is not equal to 2. And I could create a second piece for x equals 2 that fills it in. And that's why we call it removable. Okay. Analyzing a function for increasing, decreasing behavior. Let's look at another one. This is example 6, f of x equals x plus 2 squared. And that is a graph that looks like this vertex here at -2. Again, you can graph this with your calculator. It is increasing in this right part from -2. Oops, I should include that. To infinity. And it is decreasing from -infinity to -2. Graph 2, g of x, a little more complicated one. This is a rational function. It's got asymptotes where my denominator is 0. So that's both 1 and -1. Looks like it has a horizontal asymptote at 1 as well. So those dashed lines don't show up on your graph. So looking at where it is increasing, put some there and here. So it looks like all the way to 0. The problem is I've got this asymptote at -1 because -1 squared minus 1 is 0. I'm going to go -infinity to -1 union -1 to 0, and I'm going through 0. I can't go through -1 because that's an asymptote and the point does not exist there. I am then decreasing right here and here. I'm going down as I go left to right. So I always read things going left to right, and I'm going down there. Again, this is now my first part is 0 to 1. But I'm again including 0 because that's a valid point. 1 is not included because it's an asymptote. And then again, it's decreasing in the second part from 1 to infinity. The last thing we're going to talk about is boundedness. We can either have a graph. So if it's bounded, that means there's a bottom to it. It doesn't go any lower than this. If it's bounded above, that means there's a top. Or bounded below is a bottom, bounded above is a top. And bounded or fully bounded means it has a top and a bottom. So by a top, I mean something like this. There's a value that doesn't go higher. I don't need to say what it is. I just need to say it's bounded above. Bounded below has a bottom. Doesn't matter how low that bottom is, but it has one. I like to say fully bounded. Sometimes the book just says bounded. Means it has something like a top and a bottom. Unbounded has no top or bottom. That's the term we use for something that doesn't have a top or bottom. So to check boundedness, again, I look at the graph. We've got w of x equals 3x squared minus 4. And anytime you don't know what the graph looks like, you're going to use your calculator until I specify. But for now, you're using your calculator. This one looks like it's got a bottom value, so this is bounded below. My next one, p of x, equals x over 1 plus x squared. This is kind of an interesting graph. And this is fully bounded. So again, we don't have to find the points for boundedness. There's other things that we'll have to find the points for, but not for this. You can just say above or below. Okay, and that is part 1 of 1.2.